Welcome to the Explainer. Today, we're going to demystify electronic waveforms and the circuits that make them. And hey, if you've got an exam coming up on this stuff, you are in exactly the right place. We're going to make these concepts totally clear. So, let's start with a question. What do things like a radar system, your computer, or even an old-school TV all have in common? I mean, they seem completely different, right? But deep down, inside their circuits, they all speak the same secret language.
And that language is the language of waveforms. You can think of them as these repeating electrical pulses, kind of like a rhythm, or the very heartbeat inside all of our electronic devices. It's how they carry information and how everything stays perfectly in sync.
So here's our game plan. First, we'll get the big picture. Then we'll meet the basic waveform shapes. After that, we'll dissect the most important one, learn how they're actually created, and then we'll finish up with a super fast recap to make sure it all sticks.
All right, let's dive into section 1. Let's really get to the bottom of this. When I say heartbeat, I'm actually talking about a very specific type of signal.
Okay, the key word to lock into your brain here is periodic. All it means is that the signal's pattern repeats itself over and over and over again. You can think of it like a steady, predictable drumbeat. And why does that even matter? Well, because that reliable repetition is what lets electronic circuits keep time and process information without getting mixed up. Without it, you just have useless static.
Now, if waveforms are a language, then the different shapes you see are basically the letters of the alphabet. And just like our letters, each shape has its own unique job to do.
And here are some of the most common letters in our electronic alphabet. You've got the smooth, curvy sine wave. That one's perfect for things like AC power and audio signals. Then there's the super sharp on and off square wave. Now this one is the absolute foundation of all digital computers. Literally, it's your ones and your zeros. And then you have other shapes, like the sawtooth wave, which creates this steady ramp-up of voltage, which is essential for things like scanning an image across a television screen. Every shape has a special purpose.
So to really understand this language, we need to know its grammar, how to measure and describe these shapes. And for that, let's use the square wave, which is basically the workhorse of all digital electronics.
This diagram right here breaks down the grammar for us. We can measure its amplitude, that's just its height or how strong the signal is. We can measure its pulse width, that tells us how long the on part of the signal lasts. But for timing, the two most important measurements are pulse repetition time, or PRT, and pulse repetition frequency, or PRF. Let's zoom in on those.
First up is pulse repetition time, or PRT. And honestly, the name says it all. It is the amount of time it takes for the wave to complete one full pattern, one full cycle, before it starts all over again.
And its partner is pulse repetition frequency, or PRF. So if PRT measures the time for one cycle, PRF measures how frequently those cycles happen. It's the number of cycles that happen in one single second, and we measure that in hertz.
Now, this is probably the most important takeaway of this whole thing. PRT and PRF are total opposites. They have an inverse relationship. That means if one goes up, the other has to come down. Think about it. If a cycle takes a really long time, that's a high PRT, then fewer of them can fit into 1 second, right? So that's a low PRF. And if the cycle is super short, a low PRT, you can cram a whole bunch of them into a second, giving you a high PRF. This relationship is absolutely fundamental.
Okay, so we know what these waves are, and we know how to measure them. But where do they come from? How are they actually made in a circuit? Well, that's where these special circuits called multivibrators come into play.
So what is a multivibrator? Just think of it as a circuit that's specifically built to do one thing: flip a switch on and off really, really fast. It uses this clever trick called a feedback loop, where it basically talks to itself to keep switching back and forth. And that constant switching is what generates those clean, repeating square waves that act as the timing signal for so many other parts of a circuit.
Now this slide. This is a perfect cheat sheet for your exam. There are 3 main types of multivibrators. And the big difference between them is the number of stable or resting states they have. These real-world analogies are the perfect way to remember them.
Let's break that down. First, the astable multivibrator has 0 stable states. It is never at rest, it's always switching back and forth, just like a blinking warning light. Then you have the monostable, which has 1 stable state. It just sits there, waiting until you trigger it, kind of like pushing a doorbell. It gives you 1 pulse and then goes back to its resting state. And finally, the bistable has two stable states, like on and off. Just like a light switch, when you trigger it, it flips to the other state and stays there until you trigger it again. And you can actually see the difference in their design right here. Now, don't get freaked out by all the components. The key thing I want you to notice is how the astable circuit on the left is a closed loop. It's designed to just trigger itself forever. But now look at the monostable on the right. See that little input line? It's designed to wait for a signal from the outside before it does anything. That right there is the core difference.
Okay, you ready? It's time for a rapid-fire review. This is where we make absolutely sure that these concepts are locked into your brain, so pay close attention. First up, astable. The A in astable is like the prefix in a word like atypical. It means not. So this one is not stable. It has 0 stable states. It's always running, which is why we call it the free-running oscillator.
Next, we've got monostable. Mono means one. Easy enough, right? It has one stable resting state. It sits there and waits for a trigger. And when it gets one, bam, it delivers a single pulse. And that's why its nickname is the one-shot. And finally, bistable. Bi means two. It has two stable states, on and off. Just like a light switch, it flips to a new state and stays there until you tell it to flip again. We also call this one a flip-flop.
All right, let's test that knowledge. First question, what type of multivibrator does not have a stable state? Which one is the free-running oscillator we talked about? It's the astable multivibrator.
Okay, next up. What's the nickname for the monostable multivibrator? You know, the one that gives you a single pulse every time you trigger it. Remember, it gives you one shot. It's the one-shot multivibrator.
And for our last question and our biggest takeaway, what is that fundamental relationship between a waveform's frequency, its PRF, and its cycle time, its PRT? It is an inverse relationship. As one goes up, the other absolutely must go down. If you can master that one single concept, you've got the key to understanding all periodic waves.